get going here. Hi, everybody. Welcome. I think everybody knows me. For those of you who don't know me, my name is Dave Messenger. I'm director of the center. Welcome to our first Wednesday afternoon seminar of the spring semester. Thanks for braving the cold. Apparently, it's only going to get worse over the next few days. I don't know how many people just saw that little thing that probably came across your phone saying we're under a winter storm warning through like next Monday at 6 o'clock or something crazy like that. So, anywho, welcome back for those of you that went to Florida or someplace for the winter break.
Or you can come back.
That's right. So I'm very happy to introduce Dr. Maryam Rahnemoonfar from Texas A&M Corpus Christi, who was brave enough to come join us during the first couple of weeks of January. Dr. Rahnemoonfar is an assistant professor of computer science in the School of Engineering and Computer Science at Texas A&M University in Corpus Christi. There, she's the director of the Computer Vision and Remote Sensing Laboratory called the BINA Lab, which we were just talking about. Before joining Texas A&M, she was a visiting scholar at the Data to Insight Center at Indiana University and an assistant professor in the School of Engineering at Isfahan University. She has an interesting, very interdisciplinary educational background. Her bachelor's degree is actually in civil engineering from the University of Isfahan. Her master's degree is in remote sensing engineering from the University of Salford in Manchester. And her PhD is in computer science, remote sensing, that's also the University of Tehran. And then her PhD is in computer science from the University of Salford in Manchester. So please help me welcome Maryam.
Thank you so much for inviting me to this emerging science seminars and also for a nice introduction. So yeah, I want to give you a little background about my multidisciplinary area because people always question me, what is the relationship between civil engineering and computer science? So yeah, I started with civil engineering. I chose civil engineering because in high school I heard this is the discipline that has most of geometry and mathematical courses, and because I loved geometry and mathematics, I chose civil engineering. But I'm coming from beautiful and historic town called Isfahan, and we have beautiful bridges and buildings, so I didn't want to build ugly and modern building. So what I did was reverse engineering. So my main goal was to study those buildings. So for my capstone project in undergrad, I took these analog cameras. We didn't have digital camera at that stage. And I created 3D modeling of this building and document the patterns that we have in those buildings. So I mainly focused on photogrammetry part of it. And then for my master's, I did remote sensing, where I was working with radar. Again, I do care about our environment and preserving it. So with SAR interferometry, this is, for example, a SAR imagery from an area. I could do earthquake monitoring and also 3D modeling, but I'm mainly working on developing some mathematical algorithm because in radar interferometry, SAR interferometry, the main issue that we have is phase unwrapping. So the goal was to unwrap the phase, and because the equations in a special domain are very slow, I transfer it to Fourier domain and then also to time frequency domain in wavelet domain and solve my equation much faster. And then because of some reasons, I couldn't continue remote sensing, so I did my PhD in computer science, and I was working, again, I have interest in cultural heritage, so I was working with this old manuscript, and we were working with 25 national libraries, including Library of British Library of Netherlands, Germany, those big libraries, and the project was improving access to text. So the goal was to develop OCR for this Gothic manuscript or for this old manuscript and newspaper. And my role was mainly text line segmentation and also dewarping, given all of these artifacts that we have in this. So as you can see, the common theme between all of disciplines that I have done is imaging sciences, and I'm very honored to be here and talk about my my imaging science research. So first, I will talk about this big data research in polar region that I'm currently working. But also, I will talk about the deep learning challenges and opportunities that we have currently facing in our projects, and some of our AI solutions for various applications, because this algorithm can be applied in different discipline and domain. And again, from my multidisciplinary background, I would like to work and apply them on different domains like precision agriculture, Amazon robotic warehouse. This is another grant that I got last year from Amazon. Ice interlayers for UAVs. We have one of the 7 UAV test sites in the nation. So we collect lots of UAV imagery, and I am mainly interested in the data analytics part for counting and detection of animals, mapping, flood monitoring. And also I have worked with sonar sensors. Sonar are very similar also to radar. So for underwater monitoring, and also a little bit on precision health, because we are having also a new initiative in our university for aging in place centers to allow elderly people to live in their home, and we'll add some technology to be able to kind of monitor their health. And then I will talk about conclusion and future works. So about the first project, navigating Arctic and Antarctic. As we know, global warming has serious effects to our environment. Everywhere I'm going, they say, oh, this winter has been much warmer, the same as Rochester. So we accelerated loss of ice from Greenland and Antarctica has been reported in recent years, and it can have considerable influence on sea level rise and altering ocean currents, and can put millions of people at risk, especially people in coastal areas. So our university is in little island, and in a few years it can disappear, so we should be a little bit careful. So the Intergovernmental Panel on Climate Change estimate that the sea level could increase by 26 to 98 centimeters. So as you can see, it is a large range in predicted sea level rise, and all of this is because we don't have a good understanding of bed topography of the ice sheet. So that is why NSF have this new program. It is one of the 10 big ideas in NSF to navigating and studying the Arctic. So one of our goals is to calculate the thickness of ice. It's important for sea level and flood monitoring, and also the shape of the landscape beneath the ice. So how can we get information about the bed topography? What kind of sensors can penetrate through ice?
Radar.
Radar. So radar actually is the only sensor that can penetrate through ice and or through soil and give us information about the topography of what is beneath. So as a human, we can only see the surface, or any other sensor can only see the surface. Only the radar can penetrate and give us information about it. So as you may all know, radars are active sensors, so they provide their own energy. They are side-looking distance measuring system. They are measuring the time delay between the transmission and reception of a pulse. And as you can see, microwave, kind of, they are covering the larger wavelength comparing to visible. So as human, we can see only this tiny part of electromagnetic spectrum. But radar, first of all, they cover lots of area, and also their wavelength is much bigger. So for New Year student, what do you think is the main reason that ice can penetrate? Why radar can penetrate through ice? Because of this, because of this big wavelength, all right? So visible is only this part, but radar has larger wavelength and it can penetrate. So actually, for optical images, they are easy to understand and interpret, and as you can see nowadays, everyone or most of people working on optical, but the limitation of optical is obscured by cloud or smoke, and also it's limited to daylight. But radar, because it is active sensor, you can get information during night, during cloudy and foggy condition. So now self-driving cars company actually invest a lot on radar sensors because they don't want to limit their self-driving car only to bright kind of scenario. They want to work in foggy and also during night. So radar, because of being active, is all-weather imaging capability. LiDAR also is active sensors, but it doesn't have that much of wavelength. And radar is very sensitive to geometric shape, surface roughness, moisture content, so we can get all of this information from radar. And it, as I said, because of the large wavelength, it can penetrate, and it also covers several octaves. But because of side-looking nature, the interpretation of radars are complicated, and this is why we have only few experts in this area. So actually our data, our ice data coming from Center for Remote Sensing of Ice Sheet. They were funded by NSF in 2005, this big center. And they have lots of projects from NASA, and they are actually leading the NASA Ice Bridge mission. CRISIS has collected 1 petabyte of data since '93 using multiple radar sensors designed for shallow or deep imaging, and they add 100 to 150 terabytes per year. And also the recent large-scale radar survey of Greenland and Antarctica have revealed some internal ice layer on a continental scale, so this is very important. But as we all know, Arctic and Antarctic fieldworks are very, very expensive, and all of this data from '93 has been collected. But because of kind of difficulty of working with radar images, actually there have been a tiny bit of research. So, actually, when I started, when I was in IU visiting, I gave a talk about SAR interferometry, and one PhD student approached me, and he was working on this project, a similar project in Indiana University, and he had no help on radar, and that is when I kind of connected to this group and University of Kansas, and we were working for several years until we get this grant. So this is, for example, this flight line. This is from Arctic, and they collected different radar, like Q-band, snow radar, accumulation radar, and radar depth sonder In Antarctica, they have less data. As you can see, their flight lines are much sparser, but still they have lots of it. So we have lots of data. So another big idea in NSF, one of the 10 big ideas, is working with big data. So my research actually cover both area. That is why I applied for big data research funding, and because also navigating the Arctic is one of the 10 big ideas. They love the project. They funded the first time that I applied. So we have in this project, we have heterogeneous data set. We have different type of radar, like multi-channel coherent radar, depth sonder, SAR, accumulation radar, snow radar, Cuban radar, USA radar, 3D imaging. So my collaborator, University of Kansas, are from electrical engineering department, and they develop their own radar systems. And we have also LiDAR, seismic, and optical. So this is, for example, one of the images that we have. So can you guess what is this?
The bed. The bed?
Yes, exactly. This is the bed topography, and this is surface of ice. So yeah, for example, for this one, it is 2,000 meters, so it can penetrate and give us this information. So this is flight line. So our airplane is moving in this direction, and this is the ice sheet, bedrock, and this is distance below the aircraft. But with a snow radar system also, we can collect different layers of snow. So for example, now in Rochester, you can only see the surface. Maybe with radar, we can see different layers of snow that has been collected, especially in Arctic and Antarctica. So these are, can you see how many? So there are around 30 layers of snow in this, and so 1, 2, even for human, it is very, very hard to detect and track them. And it's very, very important for people to be able to kind of detect those. They have also 3D imaging radar that we will be working towards the end of our project with this. So our big data research questions that we have is, how can we automatically detect ice surface and subglacial topography for big data that we have from Arctic and Antarctic, how we can detect and trace the internal layers, the snow radar data, and incorporate the user feedback and also physical process. Can intelligent algorithm detect and trace the internal layers that human cannot detect? How can we visualize the subglacial topography in 3D, and how can we incorporate the physical and signal model-based approach with data-driven approach? Can we predict, actually this is a very important question, can we predict the ice thickness for subsequent years with data-driven approach, and will data-driven approaches will agree with physical-based model, and how can we combine those? Because, so for example, in researching about Arctic and Antarctic have been around for many, many years. And so far, there are lots of physical models that have been developed. And we are developing some data-driven approach, but we need to use and get advantage of both domains. We don't want to limit ourselves to data-driven approaches. So to answer all of this question, we got this 1.4 million grant. We just started a few months ago, and we have 4 years to complete this project. So I am just explaining a little bit about what we have done. Actually, we had some preliminary result before that that I want to share with you. So the challenges that we have for the first problem, detecting the ice surface and bed topography, we have a large amount of noise and clutter. So as you can see here, lots of algorithms have problem with this. And also the bed topography can be highly variable. They can be completely flat or they can be mountainous. And also we have lots of surface multiple because of ringing of radar signal between the metal, large metal aircraft and ice surface. I will show you this. So the first algorithm that we developed actually was based on level set. So level set is kind of active, the continuation of active contours, and it has, we want to find the solution of this dynamical system. It is the combination of different forces, but the level set has the problem of you need to reinitialize it manually, so we added a term to be able to reinitialize it automatically. So the data set that we used for that study was from 2009, NASA Operation Icebridge mission, and as I said, University of Kansas is working or even leading that project. And we use multi-channel coherent radar depth sonder. The resolution is 900 by 700 pixels. So we have 50 kilometers on the ground and 0 to 4 kilometers of ice thickness. And we, in this study, we use just 323 images. So this is our level set algorithm. As you can see, it can handle noise very well. So we start with some initial curve and it evolves and it will give us this contours. And we have this label data from, so human, actually the experts in that area, they manually label this, but they cannot do everything by hand, so they just pick some points and then they will do kind of interpolation. So as you can see, it cannot detect the exact one, while our algorithm was able to detect even better than the ground truth. And here is when you have clutter and also this surface multiple. Again, so we started with this initial curve and it evolved and gave us this curve. So it worked very well in most scenarios, but yeah, when we have kind of invisible bedrock or when radar cannot give us the complete picture of bedrock, then actually there is no way to stop the evolving of our curve. So it should stop here, but it will continue evolving. So on our entire data set with some visible and invisible ice bottom, we got 75%. If we focus only on visible ice bottom, we got 96% accuracy with level set. And this is the distance between what we extracted and what the human label extracted for both surface and bottom. All right. So another method that we developed was based on electric field. So we assume that every pixel is an electrical charged particle, and there are some forces between. So if you assume each pixel has some electrical charge, there would be some forces between them, and then we can use Coulomb's law to extract the interaction between them. So, but because in images, pixel signs are always positive, it means that the force would be always repulsive. So what we need to have both repulsive and attractive force, we came up with this simple equation to convert our kind of pixel value to electron or proton value. And then we calculate the interaction between each central pixel and the pixel around it, and we came up with this kernel. So we tried it first on Berkeley segmentation dataset, and this is our result, actually. And these are some state-of-the-art results. As you can see, our method was working very well. And then also we tested on our ice sheet. So because this method cannot handle noise, so first we applied some anisotropic diffusion to smooth the image, and then we applied our electric field so it can detect this ice surface and bed topography with this electric field. And then we actually extracted the projection profile for each column and got the maximum values, and then we could detect these two layers. Yeah, and we again tried on different type of radar, and our results could handle better the hidden or invisible layer, so we could improve the accuracy a little bit. All right, but none of our algorithm actually can work on these internal layers, and there isn't any single automatic technique that currently is published or working on this internal layer. It's very, very challenging, and also our current techniques, or most of the current techniques, are feature-based, and if they are model-based, and for level set or for even electrical field, you need lots of tuning, and you cannot apply it to big data that can work on any kind of region and any type of image. And our data set is very heterogeneous, so the current method cannot be generalized to internal layers. And as I said, there isn't any automatic technique that can work on internal layers. So we started with end-to-end learning. So as you know, now deep learning is kind of everywhere because of high powerful GPUs that we have, and because of massive data set. So we can apply it for image classification, object detection, scene recognition. But there are several challenges. So have you heard, or do you know what are the challenges? Students that
You don't have all the GPUs?
All right, what else? Yeah, actually, if you want to work on some low cover platform like UAVs, yeah, you cannot deploy it. What else? What are the challenges? So the big challenge especially for those of us which have lots of data but we don't have label data, is the availability of large label data. This is one of the main challenges. I have talked to many companies, especially small companies. They don't will to invest lots of time to kind of create those label data. And also, deep learning has proved that a limited amount of noise and perturbation greatly affect the performance of most of deep learning techniques. So even there was one article that even if you perturb 1 pixel, it may change your classification result completely. And yeah, so now people are just adding more depth to their network or adding more complexity, but then it will increase the computational complexity and it will not work on all scenarios. And most of deep learning approaches are designed and tested for electro-optical and human-centric images, like ImageNet data type, but they are not tested for overhead imagery, aerial imagery, or with other sensors. There are a few works, but the majority of them are in these scenarios. So some of our solutions and experiments beyond ice data, for lack of training data, actually, the first thing that we tried was using simulation. And I will talk a little bit what we did in agriculture in polar ice. And also, for lack of training data, so because units for deep learning, you will start with some random weights, some initial, you need to initialize your network with some random weights, so it can take a long time to converge. But if we start with, for example, if we combine some prior knowledge that we have with the deep learning model, it can help with the conversions. So we use wavelet and one-shot learning for our Amazon project. For noise also, wavelet can handle most of the noise, and the multi-scale fusion can do that. If we have large size images, also wavelet looks at multi-scale, so that will help. And also for beyond visual spectrum and beyond human-centric vision for aerial images, we tried CNN plus RNN. So you don't have lots of label data, but you have tiny, small label data, so you can use CNN to give some approximation, and you can use RNN to kind of improve the results. And then also we use region selection, and we also tested on sonar, radar, and RGB. So yeah, actually a few years ago, people from our agriculture department approached us, and they said, you know, we want to develop some techniques that just by taking images can count and can calculate the yield of our products. But the illumination can be various. Fruits can be under shadow. They can be occluded by foliage, and they can have, so they can also have overlap with each other. Scale can be variant, and also no label data is available. So what we did, actually, we started with very, very simplistic simulation, nothing fancy. Yesterday I saw your simulation tools, and it is perfect. No, we didn't have any of this, so we started with some simulated data, and we developed our network based on inception ResNet and some modifying inception ResNet, and we trained on this synthetic data, and we tested on real data. And yeah, first of all, it was much faster than human, and also we got very good access. So our simulation, as I said, it's very, very simple with some just, we started with some Gaussian blurring, and then we added some circles. That's it. This is our simulated data. And this is our network structure. Yeah, so as you can see, actually, in most of scenarios, it works very well. So you can, so this is the count by our algorithm, and this is the actual count. So human count is at 38, and our algorithm detected 36. And even if they are under shadow or partially are visible, still we can detect it very well. So we got around 91% accuracy, while the current techniques for counting was around 66% accuracy, and our method was also very fast. All right, so this is another simulation that we have done for ice images. And actually, we use some data-driven approaches because for simulation, for physical simulation, you need to know a lot about the material and lighting condition and atmospheric condition and all of this information. So we use generative adversarial network, GANs, to actually generate this data, because generating this is very easy. You can randomly create some curves, and then your algorithm can generate this synthetic radar data. And when we compare, so this is our input, and this is the synthetic radar data that we created, and this is the actual ground truth. So it is very, very close. We haven't, so in University of Kansas, they have some physical simulation model. We are planning to compare our data-driven simulation with physical model. But we just did a survey and asked people to distinguish between the real data and synthetic data, and most of the time they couldn't detect, but there are some quantitative criteria that we want to use. And with this, we can generate millions of data, so it will help us with lack of label data. All right. So, but for Amazon project, actually, none of this work, not the first simulation that we did, or the second. The data is very, very complex. So actually, because of our success in counting objects, we got this award, Amazon Research Award from Amazon, to be able to detect and count objects and verify them in Amazon warehouses. So these are the type of imagery that we have. As you can see, it is very occluded, and it's very, very difficult and very challenging. So these are the type of imagery that we have, and we don't have any label data for them. So for example, here, I don't know, there might be 5 objects, but as a human, you can just see 2 objects, but inventory will tell you different things. And sometimes also inventory is wrong. So Amazon researcher told me that sometimes a customer order an item, and you, based on your inventory, you think that you have this object in that specific shelf, but when you go and you want to pick it up, there isn't. So they want to develop a robot that can visually detect and count and collect objects. So because we don't have any label data for that, and simulation is very, very hard, we don't have any information about the lighting condition, about the material, anything, we cannot use simulated data. But, and actually because of this huge occlusion, what we did, we transformed our images to wavelet domain. We applied discrete wavelet transform, and then we gave this imagery to our network. This is actually the same deep count network that we developed for counting fruits and vegetables. And so we can have counting output, and also we can verify if an object A is in the shelf or not. So actually this is a kind of new research area, hybrid scattering networks, because the precise location of early layers of network is not known, is not well understood. So if we integrate some predefined geometric priors with some learned representation, the model can converge faster and it can speed up the learning. So actually Professor Mallet, who is very, very famous in wavelet domain, he has started this research, and they show that early layers of the deep network do not necessarily need to be learned and can be replaced with some predefined features. So this is the wavelet transform that, so this is continuous wavelet transform. So when you have Fourier transform, you convert your spatial domain to frequency domain and you lose information about the time. But wavelet, you have both frequency domain and time domain, or frequency and spatial domain. So this is how discrete wavelet transform works. So you apply low pass and high pass filter, downsample it on rows and also on columns, and you will get this 4 channels of information. So with that, actually we could, so for counting, first of all, counting is the most difficult problem, especially for visual question answering. So it has the lowest accuracy currently in all of the question. In visual question answering, counting is the most difficult one. Also for humans, it's very simple, but still we don't know how humans are able to count. So this is absolute accuracy and this is relative accuracy. So as you can see, comparing to very, very deep network or network with some prior knowledge, even if it is not that deep, could improve the accuracy. And also we tested on other data sets like COCO, and also it's, the error is much lower than other techniques. So these are some of the images. And so ground truth, this is based on inventory, and human is what we can actually see, because sometimes inventory is different. And as I said, so for example here it says that there are 4 objects, but as a human we can see only 3 objects, and our algorithm actually predicts 3. Or here it says there are 5 objects, but we can hardly see 3 objects, and our algorithm works with it. So we compare with this actual ground truth, but if we compare with what humans see, our accuracy can improve. And then we use Siamese network, because we have, again, almost no label data. And we use this, the truncated version of our DeepNet to be able to verify. So now we can ask question that, for example, is blah blah book is in this, and the prediction is yes, and our ground truth is saying no. But there are most of the cases that our algorithm can predict as well as what human predicts. So again, with our the Siamese network and our WNet network, which is combination of our deep count and wavelet, we could improve accuracy comparing to other deep networks. All right, so now back to ice bridge mission. Yeah, we applied wavelets, and also what we did, we looked at the multi-scale. So if we have this network, we look at the side output, and because of this multi-scale, it can handle noise better. So it can detect this ice surface and bed topography, and also it can work on larger size images that we usually have. Yeah, so this multi-scale network, or the fusion of multi-scale intermediate layers, improve the deep learning performance in terms of accuracy, and also it enables the processing of large and high resolution imagery. So yeah, we compare it with something. We haven't compared it with our level established because this is on different data sets, but I think we improved a lot the accuracy compared to others. For ice internal layers, as I said, there isn't any single technique that can work automatically. So our this big complicated data set combining wavelets with neural net works fine. So this is the ground truth label, and actually it doesn't show here, but in some of our images here also there are some internal layers that human cannot detect, but our algorithm could detect, but it still is not perfect, and we, as I said, we have just started working on it. We have another 4 years to work on this. So, I'm sorry, I need to finish it quickly. So beyond human-centric photographs, we also work a lot with UAV data set. So actually most of ImageNet data are this type, and the images that we have, our aerial images, are like this. So can you detect the cattle in this image? Yes, so these are some tiny, so first of all, if you look at horizontal view on your object, you can see different parts of the object. You can see the head, the legs, and the tail. Or so even for human, it's much easier. But when you look at top, you will just see a flat and a small view of objects, and it's unbalanced classes. So here, the object and background are almost balanced, but here, the background and object is very unbalanced. We have large size images, and again, we don't have label data. So this is the data that my colleague collected from one of the big ranches in Texas, because in Texas, detecting and monitoring animals, especially cattle, are very, very important. This is the biggest issue, that they cannot monitor this by human, and also airplane will create some noise. So recently they have tried UAVs, and also cattle don't like the collar, GPS, etc. So what we did in this, actually I don't have time to go to details. So what we did, we used one network to kind of find some of the regions. So we did region selection, and then another network was able to focus on that area and be able to count. So this is the ground truth, and this is what we were able to detect and count. We also worked for urban mapping. Some insurance companies are interested to detect buildings, and also the roof condition. We haven't gone through roof condition yet, but yes, we developed some CNN, RNN techniques to be able to detect this. And also last year we had terrible flood because of hurricane in Houston. So this was kind of easier problem. We had only 2-class flood or non-flood, and again we were able. So this is the ground truth, and this is our results. Again with this one we developed CNN and RNN. Here, so I had another colleague in University of Texas, Rio Grande Valley, and they collect lots of sonar imagery, and they were interested in detecting the holes in seagrass, potholes. I don't know exactly why they are interested, but one of the reasons is to see where fish are collected, because fishing also is very important in Corpus Christi. So they wanted to detect those holes in seagrass. So yeah, we, again, our this network is a little bit complicated. I'm not going to details. So we were able to detect the holes, but still we cannot detect the kind of boat trace, because this is also important for them. They want to catch the illegal kind of boats because it disturbs the seagrass. So our algorithm couldn't detect this, although we could detect the small holes, but we couldn't detect this path. And one of the reasons is that with deep neural net, you will work on, although we develop algorithm to work on larger images, but still, because of heavy computation, you cannot have the big picture of the image. So still, we are working on this. And yeah, as I said, with RGBD camera also, we were interested to detect fogs, elderly fog detection. So we use some 3D convolution techniques to be able to detect when fall happens for elderly people, for aging in place, and we are trying to predict when this will happen if we can monitor the some years. So I explained about our plans for big data from Arctic and Antarctic. Actually, we just are in the very first phase for determining ice thickness and internal layers, but we want to predict for subsequent years and for 3D modeling. Our focus so far have been on mainly data-driven approaches, but as I said, there are lots of physical model approaches that we want to combine and compare to get advantage of both. And also, we need to, so as I said, human cannot detect some of the layers. So our question is that if we provide some information to machine that are not available to human, like phase information in radar, can we get more insight to the data and can we extract more? So I talk a little bit of the challenges in big data and machine learning. We have heterogeneous sensors, we have large image sizes, we have unbalanced classes, we have lack of label data, and we have lots of noise. So yeah, actually so the solution that we had so far was working with simulated data, with multi-scale, with CNN, RNN, with region selection, and with deep hybrid spectral network. So in future, in addition to working on applied machine learning for our current big data, I am interested to work on this theoretical machine learning, actually designing and testing the deep learning models, not only as a spatial domain, but also in time frequency domain. So we have some result in frequency domain, and it is much faster. And the accuracy is going down a little bit, but our result shows that wavelet domain is much a stronger domain, that we can have both frequency and time domain. So frequency domain may be excellent for a stationary signal, but because in real scenario we have non-stationary signals, so we need to work with wavelet. So actually what we have done so far is to combine this special domain of deep neural net with wavelet domain. We have done a little bit for internal ice layers. Actually, we have done a little bit of physical model or mathematical model to supervise our neural net, so we can get some insight what are these internal layers mean. So we can supervise it, but the next phase that I'm planning to do, and actually this is it's very, very early stages, to transform and solve our entire model in wavelet domain. This is very, very challenging, which I'm currently working, but we got some research funding from machine learning award in Amazon. So yeah, so I think wavelet domain, because of the sparse representation, it can speed up the numerical operation because of the multi-resolution. It can work. It can handle large scale images with higher accuracy, and because of the space frequency locality, also it can distribute the effect of the operation both especially and in frequency domain. I think I can continue kind of getting funding from DOE. Actually, DOE loved my proposal, and I hope I can get it in the second one, and of course others. And yeah, I love to work with multidisciplinary area as I have done so far with agriculture, library science, biology, nursing, civil and engineering, and I would like to acknowledge all of the research funding agency and all of my collaborators and also all of my students. I don't want to advertise, but I do have some PhD position available if you are interested. And thank you so much for your attention.
All right, we have time for a few questions, not too many, but yeah.
Yeah, I have a question about this discrete wavelet transform. As you said, it's very beneficial for example, signals when it's important to maintain time as well as frequency. But why did it perform better for static images in Amazon warehouses?
All right. So when I say time, frequency. So actually, all of our signals are non-stationary signals, because if you don't care where your object is, if you just want to do classification that I have this object, Fourier domain is perfect. But if you want to know where this object is located, so locality, then you need to have information about both time and frequency, or time and spatial domain. So this gives you information about both content and also the locality. That is why it is important.
Thank you.
So I was curious, on your last chart, you talked about supervised sort of learning, where you had the features that were learned in this way and the wavelets that you seem to be implying that they could inform the features, right? But can you think of are there other things that could be used to supervise it, say, in my case, spectral, right? Instead of doing those spatial wavelet transform, is it possible to sort of inform that learning by other information that's coming at different levels?
Yeah, actually there are some research on deep supervision. So because with backpropagation, we mainly supervise the last layer of the network. Right. So now the idea is that what will happen with internal layers. So if with some kind of information you can supervise the internal layers, my idea is to supervise it with some mathematical model, time frequency model, but sure that will probably work.
Yep.
You quoted a guy named Malik in one of your slides, and he said that it doesn't matter, like at the early layers of a network, if the weights are learned or not. How did that help in your project?
So no, it doesn't say that it doesn't matter if it learns or not. It says that the early layers of network, that their function is not known, and it's probably not learned. So the idea is that instead of using some initial and random weights, why not initialize it with something that we know? So for example, if your physical model works and it's not perfect, why not get some output from your physical model, and then maybe you can apply the network on top of it. So we don't need to start everything from scratch. If we have information, let's use it.
Does that help with small data?
With a small data, actually, it is. So they show in their paper that with a small data, it is most helpful than if you have. And yeah, if you have large data, so your algorithm can converge, and you don't have much problem. But the problem is when you have small data. Yes.
All right, so just a reminder, we have, I believe, I hope, cookies and coffee and stuff waiting for us in the atrium. Let's thank our speaker one more time.